Thank you for that kind introduction, and thanks for having me here and coming tonight. This is actually, I didn't raise my hand, but this actually is also my first time at Mount Wilson. I've only been the director of Carnegie Observatories for a few months, and so this is actually my first trip up here, and I'm really glad to be here. The 100-inch is an amazing instrument. Before I was here, I was a professor at New York University for about 25 years and an observational astronomer, and most of my work over that time has indeed involved the Sloan Digital Sky Survey, which actually also the observatories, the Carnegie Observatories, has for the last 10 years or so been a really integral part of that project as well. And so I'm going to describe all that. And, as Dan alluded, as a digital sky survey, SDSS sort of led a transformation of astronomy, which I want to describe. And it's a transformation based on new technology. And so I wanted to put that in some historical context. And so I didn't quite go as far back as the Babylonians, but I thought I'd start with Galileo, who's the first person to take a telescope and point it at the night sky and write down what he saw. And he discovered, just in the first few weeks of looking at the sky with the telescope, a number of new and amazing things. I'm only going to describe one of them, which involves the Milky Way. The Milky Way, you will know, is this band of light across the sky. It looks diffuse. All the stars look like little points. The Milky Way looks like some diffuse band of light. And so for, millennia, people didn't really know exactly what that was. They didn't even know what stars were. But the question was, is the Milky Way something different, or is it just a bunch of really faint stars? And what Galileo was able to show was that the Milky Way was actually just a conglomeration of stars. You point a telescope at it, and you see in his diagram that he drew here, you can see the big stars are the ones you could see with your eye, and the little stars are the new ones he saw with the telescope, the ones he was resolving and showing that they were what made up the Milky Way. And so over the course of the next 100 or so years, people came to understand that the Milky Way was a big conglomeration of stars and the stars were things that were similar to our sun but very far away, and somehow they're in this flattened distribution that we're somewhere in the middle of. That's sort of the picture they had. And then outside of that, nothing. So the picture people start to develop from this is that there is the galaxy, the Milky Way, and it's sitting in some big, vast, empty space, and that's all there is. That's the universe. However, this did not, he was hopeful that we would be freed from the wordy disputes upon the subject of galaxies, but trust me, we were not. So technology marched on, telescopes got bigger. This is the Herschel's telescope, William and Caroline Herschel. So this is a large reflecting telescope, one of the really early reflecting telescopes. And they're now able to see really faint things. And guess what? They see some of the really faint things are also fuzzy, kind of like the Milky Way looked fuzzy. And what they call them nebulae during this time period. All these things, which there's probably like 7 different types of objects here, but at the time they didn't know what they were, so they were all categorized as just nebulae. And some of them became categorized as spiral nebulae, like this one and that one. Maybe that one, maybe that one. Some of them are spiral nebulae, and that's how they're thought of. But it's not clear what they are. Are they inside of our galaxy, and they're just some blob of gas inside our galaxy? Or, as some people come to believe, are they super distant galaxies that are outside the Milky Way, so that the Milky Way is not alone, they're distant galaxies? So this is a hard question to answer with the technology of the early 1800s, but technology marches on. And there are 2 really critical pieces of technology that come in, one of which is photography, that suddenly you're able to not just look through a telescope and make a drawing. Even if you're a good drawer, as opposed to Galileo. Even if you're good at drawing, like this isn't exactly what you want to study scientifically. It's really nice to have a photograph you can keep, and you can look at it in the morning when maybe you're less tired and it's not dark, and you can keep it and observe and look at it next week and the week after that, and you can give it to somebody else to look at. Photography is great because you can store these things and study them forever. We still have the first astronomical image that was taken photographically. Actually, we don't. Daguerre did one too, but his lab burned down. But Draper's we have. The other important piece of technology was spectroscopy, breaking up the light that we see into its different wavelengths. And so what this shows is it shows 7 different stars, and along the horizontal axis here is wavelength. And they've broken up the light. William and Margaret Huggins have broken up the light into red light, less red light, less red light, blue light. And all of these features are showing you how much light is being emitted by the star. And in this image, the bright areas are, the star is bright, and the dark areas are absorption features. And those features are signatures of atoms and molecules in the surface of the star. So like this set of features in Alpha Lyrae, this is the star we call Vega, those are all features of hydrogen gas. But I want to point out just a pair of them here. These 2 features, the ones labeled K and H, these are signatures of calcium, in just a trace amount of calcium in the atmosphere of the star. And so you can learn a lot from this. You can learn what elements are in the star. You can learn the age of the star. You can learn the temperature of the star. There's a lot of information in the spectra. And so people went to town in the 1900s. They, including here, this is the 100-inch, which you will see or have seen. This is Milton Humison taking exposure. He's opening the shutter here, and he has a glass plate here, and he's exposing. And they did this. They took images, they took spectra, they studied the sky, and they filled our basement with glass. So there's our basement, and in fact our attic, have like a whole ton of glass plates that people were able to go back and study at their leisure. People came here and to Palomar and collected this data. Some of them took it home with them, you know, wherever they were coming from, and had it to study. But they had to have the glass plate with them. Nevertheless, they could do some really good things. So this is a famous story, and I think it's in my contract. I have to tell this story. But in the 1920s, Edwin Hubble is looking at one of the spiral nebulae, the largest spiral nebula in the sky, called Andromeda. You can actually, in a dark enough site, you can see it with your naked eye, if you know where to look. So there it is in this glass plate over here on the right, and he's studying the variability of stars, partly to try to figure out a way to figure out how far away it is. And he notices a star here, which you can't see, but he could see on this glass plate. And he took many, many glass plates. Again, you can compare them night to night because you have the glass plates. And he could see it varying. And it varied over the course of a few weeks. Brighter, fainter, brighter, fainter. So that's interesting. He seemed very interested in this. He has an exclamation point. And the reason he was so interested in this is because a few years earlier, Henrietta Leavitt had been studying stars in the small and large Magellanic Clouds. This was data that was taken in Peru, in Arequipa, and these plates were shipped up to Harvard, where Henrietta Leavitt was, and where they were using the Draper fortune to do astronomy. And what she found was basically the same type of star, and each of these pairs of points is one star. And this is just showing this star, it gets this faint, and then it gets this bright, and then this faint, and this bright, and it varies with a period of about 30 days, about a month. And so stars that are varying with that period of this type are this bright, forget what these numbers mean, but this bright in the Small Magellanic Cloud. At the time, the Small Magellanic Cloud was kind of known to be in the outskirts of the Milky Way, not quite part of the Milky Way, but but not very far away, not like its own thing. So Edwin Hubble finds the same type of star and asks, with the same period, about 30 days, and guess where that lands on this plot? Well, he didn't make the plot, so I had to make the plot. But if you extend this plot downward, these stars land here. So same type of star, but it appears much, much fainter. Therefore, it's fainter because it's further away. It just appears fainter, but it's the same intrinsic luminosity. And this means it's about 200 or 300 times fainter. That's what these numbers on the sides mean. And that means it's like 15, 20 times further away. So if the SMC is on the outskirts of the Milky Way, Andromeda is just way out there. In fact, we know now it's about 2 million light years away. It's a separate galaxy. It's the nearest large galaxy, the nearest galaxy similar in size to the Milky Way. And because we're astronomers, we're like, well, one of the spiral nebulae is really far away. They're probably all far away. And believe it or not, that turns out to basically be true. And so all of these things that Huggins is looking at, those things, the spiral nebulae among those, are distant galaxies. So, same time, Milton Humason, again here, is taking spectra of galaxies. He's looking for Doppler shifts. So, Doppler shift of sound, that's when cars coming towards you, it sounds like this. It's going away from you, it sounds like this. Right? Lower frequency, longer wavelength waves when something's going away from you. Light does the same thing. Lower frequency gets to lower frequency, longer wavelength light when something's moving away from you. So these are spectra of galaxies. Galaxies, as Galileo showed us, are made of stars. So the spectra of galaxies look like the spectra of a bunch of stars. So they have the same features. For example, if you look here, Humason has labeled this K and H. These are these same calcium K and H lines. Here he's plotted the spectra the opposite way. So the bright part, the middle of these spectra are the stars. The lines on the outside are just like calibration points. Ignore those. But these white bands are the bands of absorptions. The ones that Huggins showed as dark are now shown as bright just because they reversed it, because astronomers are annoying that way. But these two features, when you look at fainter and fainter galaxies, they are moving more and more to the right. Therefore, the galaxies are moving faster and faster away. In fact, this one is like, 5–10% the speed of light. So going very fast away from us. And that turns out most galaxies are moving very, very fast away from us. So Hubble looks at the same things, and he decides to plot this velocity against the distance. He didn't really have a way to measure distance. It is too embarrassing to astronomy to explain how he got the labels on this x-axis. It was very, very crude. But it worked well enough, and well enough that he saw this correlation, which again turns out to be correct. The slope wasn't correct, but the fact that there is this relationship is correct. The speed of a galaxy depends on its distance, and it's linear, so the velocity is some constant called the distance. And Hubble was not a modest person, I hear, but he did not actually, I think, call it the Hubble constant himself. But this is what is called the Hubble constant, the h0 that relates these two things. So if you knew the distance of a galaxy, you could predict its velocity. But actually, the distance is a really difficult thing to measure. It's really hard. Distances to galaxies that are this far away, like real good distances, didn't happen until the 1990s. So these things are really hard. Velocities are easy. Like you just read it off this plot. It's super easy. So if you want to map the universe, measure velocities, and that will tell you the distances to the galaxies. So that's important to the Sloan Digital Sky Survey, which I promise I will get to. So technology marches forward. For 100 years, people are using photographic technology. But once people understand silicon, transistors, semiconductor technology, people can make digital cameras. And so by the mid-70s, they have the first digital cameras, and guess what they do? They point them at the sky, because it's cool to look at the sky. In fact, they look at the same object John Draper looked at, which is the moon. This, though, is a really small patch of the moon. So you're seeing sort of craters and other features on the surface of the moon. It's really zoomed in. But this is an image of the moon. And the really nice thing about digital is that you can take this data and put it in a computer, and your computer can do your analysis. That's great. Also, you can share it. I can send you the data, and you the data, and you the data, and you the data. It's not a glass plate. You can send it anywhere. You can share it across the world. And so, in fact, you can launch a telescope into space, like the Hubble Space Telescope, and you don't have to drop glass plates down to Earth. You just, you can just telemeter the data down. So people in the 90s start making these big digital things. And one of them is the Sloan Digital Sky Survey. And as I said, a key thing here is that now, we get the data from the Sloan Digital Sky Survey, but we can share it with anybody, so we do. So this data, in fact, is available. I want an image and a spectrum of a galaxy. This is a slightly different way of looking at a spectrum. It's just showing the brightness as a function of the wavelength here numerically. And this is just an image of that same galaxy. And you can just go to the web. And we have the data there because it's digital. It's easy to share. And you can collect a lot of it. So how did this happen? So took from the 70s to the 90s for this technology to really get going. But by the late 1980s, it was clear it was coming, and people were experimenting with small cameras. And a small group of people figured out that they could do a really big survey if they built the right camera. They could image a third of the sky, and they could take spectra and get distances to 1 million galaxies. So one of these is Don York, who was the first director of SDSS. He's down in the bottom left here. I've lost my cursor. That's Don York right there, smiling in this early collaboration meeting. This is Rich Crone, who's one of the other masterminds. This is Jim Gunn, someone mentioning earlier tonight, looking very Galileo-like with his beard. He is probably the closest person I've met to Galileo, actually. He is a true genius. This is the camera he built. He built it with Connie Rockesy, who was first an undergraduate and then a graduate student at the time. She's at Santa Cruz now. And she looks a little bit like Humison in that picture. She's at the back of the telescope. But actually, when the telescope's working, you move away from the back of it these days. This is the camera going into the focal plane of the telescope. So they planned out this survey, and they had a good plan. They were going to do it in 5 years for $12 million. They did it in 10 years for about $80 million, which was a bargain. In fact, you look back and you're like, they were nuts, like 5 years, $12 million. But it was a very stressful time. I was a graduate student at the time, and I remember sort of listening in on the meetings that were happening, and people were really stressed. But, across this, at that time, pretty big collaboration of 8 institutions, they learned to work together and make it all happen. Here's an early picture. They learned to have a little fun. I believe this is Rich Crone sticking his head out. I don't know if Charlie was there, but this is while they're building the telescope. There's a really great book about this by Ann Finkelbeiner that goes through the whole history. There's so many good stories from that time, and Ann tells a few of them. The rest, I think she felt like she couldn't tell. But it's a really fantastic book. So what did we do? We took images of the sky as the first thing. So Here's an example, just really zoomed in on a particular part of a galaxy. This is a star-forming region. If you zoom out a little, you see it's in a particular galaxy, Messier 33, also quite a bright galaxy on the sky. You can see it through binoculars rather easily. And then if you zoom out further, we have a larger image. And then this on the bottom is giving you a scale of the total area that we imaged, which was, again, about a third of the sky. And the image on the bottom isn't a real image. It's an image where I've subtracted all the stars. So this is just the image of the galaxy light. And so what you see is that it's sort of a roughly uniform distribution of galaxies on the sky, but there's some interesting structures. There's a big clump there. There's some empty-ish looking regions. It doesn't look quite even. But we're only seeing this distribution in 2 dimensions projected on the sky. We're not seeing the 3rd dimension. So we want to see the 3rd dimension. But that means we have to observe 1 million galaxies. And that's a lot of spectra to take. So we have to do it carefully. We can't do it one at a time. We have to do it like 640 or 1,000 at a time. First we did 640, then we made a better system and did it 1,000 at a time. And this is how we did it for about 20 years. We used these, what we call plug plates. I'll show you what they are. So they are big metal plates where you drill holes in them. This is Ken, a machinist at University of Washington. And he's very, very carefully putting this thing in. There's a drilling machine here, which is very carefully calibrated, you can see here. And this thing, you know, the drill comes down, the drill just goes up and down, and there's a table which the plate is moving on, and it's drilling holes in the plate. And those holes need to be drilled with about 10 micron precision relative to each other. So they have to be, so that's why there's all that fluid. That fluid is there to keep it all at the same temperature so that the plate isn't expanding and contracting. And you can see the holes there. So you get all those holes in the plate. What do you do with them? Well, you've got to take optical fibers and plug them into the holes. So you ship the plate down to the observatory, and at the observatory, in a little room called the plug room, there's a couple of people whose full-time job during the day is to plug these holes. This is a time-lapse video. And this is 1,000 fibers this person is doing. And they can do it in 45 minutes. They're really good at it. They're the best people in the world at doing this. So you prepare maybe 10 plates like this, all with 1,000 optical fibers in them during the day. And then what do? You've got to observe them. So you've got to get them into the focal plane of the telescope. So this is Karen Kinamuchi, who was an observer at APO for a really long time. Each of those little cartridges on the left there has a plate in it with all the fibers. She brings it out to the telescope, opens up this big shed. That's the telescope. That's the focal plane of the telescope down there. She takes an old cartridge out, puts a new cartridge in. This is also time-lapse. Brings it back, does that, takes a bow. Very good. Then they're preparing the telescope for the observations at night. You know, comes dusk. Moving around, making sure everything's right. Now they're observing. And you can see, this is time-lapse, so you're seeing the sky go by really quickly. They observe for about an hour on each location on the sky that they observe with one plate. There we go. And then they're done. They take some calibrations. They change out the plate. Look somewhere else. And you can even see the telescope following the field. This is a little bit later in the night. Some annoying clouds there to the south, but we're not looking through those. And then I'll do this for a while. And now they're going to change out the plate, take some calibrations. There we go. Nice. Then you've got your data. What do you do in the morning? Well, you ship the data over wire. We used to do it with digital tape, but now we do it over the internet to the University of Utah. There's a big bank of computers in downtown Utah, in downtown Salt Lake. All the data goes there, and there's a set of people who are in charge of making sure it all gets analyzed. This is that set of people, plus me. I didn't have any responsibility. I was just in the picture. But these people do this. It's a small group of people. If only this group of people were using the data for science, they would write a few papers a year. But they don't. They work in a huge collaboration with which they can share the data because it's electronic. And so there's 70 institutions now across the world that are part of the collaboration. The data goes to them. So that group of people writes maybe 100 papers per year, advancing science. Every couple of years, or every year or two, we release the data completely publicly. It goes to astronomers. It goes to the general public. It goes to educators. And the rest of the astronomical community writes 400 more papers per year. So by releasing the data, we've taken what is generated by a relatively small group of people and produced an enormous amount of science. And that is really the key thing. That is the reason it was so transformative, is because it showed that that would work and that the people doing the survey would get faculty jobs like me, and that their data wouldn't be scooped and they wouldn't lose credit. Everybody who made the survey work got a lot of credit for it. And so it was a real success in showing that an open data philosophy could function. You could succeed, and tons of science would get done. Now, the plates themselves, once we use them on a field, we can't use them anymore. We've already observed that field. I mean, we could observe the field again, but what's the point? So we've made like 13,000 of them. So we have to do something with them. So some of them, actually a lot of them, and this is the main use, hundreds of plates have been sent to middle schools and high schools. Basically, we send them to one of the collaborating institutions. A bunch of teachers come in. There's a curriculum training thing. We teach them about the plates and how to use them. There's a bunch of materials. They go through, a few days of that. Then they go back home with a plate that's an artifact in their classroom of a particular place on the sky that their students can look up the spectra that were taken with that exact plate. And so it's an amazing program, Plates for Education. Anna Maria Wyman's here, who works in Scotland, is very excited about this. So there's like hundreds of schools in Scotland that have spectroscopic plates. It's a very strong concentration of plates. People do other things with them. So you can make chandeliers. This is Josiah Milkenny. These are based on the Metropolitan Opera of New York chandeliers. Whenever I go there, I'm like, oh yeah, it's like the spectroscopic plates. You can make coffee tables. You can make coffee tables and then put the Millennium Falcon on them because you're an astronomer. You can have, your spouse might be an artist and can make a mock-up of the telescope made out of plates. So there are many creative opportunities here. So, but we also do science. Just like Humason, we want to get the redshifts of these things. So again, this is the spectrum of one of these galaxies. Here's a picture of the galaxy. We have a spectrum of the center. And here is, again, the amount of light coming from each wavelength. Here are our friends, K and H, those lines of calcium here. But there are a lot of other features too. And all of these features are going to shift to the red if the object is moving fast away from us. This one is moving, kind of fast away from us, 5,000 kilometers per second. That seems pretty close by. 160 million light years. This one is fainter, therefore it's not surprising. It's further away. It's going about 30,000 kilometers per second, a tenth the speed of light. So it's like a billion light years away. And you can see all of these features have shifted to the red. Those K and H lines are shifting to the red. That's how we get the redshifts, and that's how we infer the distances, and that's how we make a map like this. And so now that two-dimensional map, this is still a two-dimensional map, but it's a different 2 dimensions. This is looking at a slice through our 3-dimensional map. We are at the center here, the redshift, and therefore the distance is sort of the radius away from the center. These directions that are black because we just haven't looked there. That's because the galactic plane is in the way. But here you can see where all the galaxies are. And you see these giant voids, you see filaments, you see all this structure. You also see the points are colored by the actual color of the galaxy. I mean, it's not like the actual color your eyes would see. It's just like a color that's related to that color. So the outer ones are red, the inner ones are blue. The outer ones are red because the further away ones are really the more intrinsically luminous ones, and those ones tend to be red relative to the lower luminosity ones. You can also see if you squint that the clumps of galaxies tend to be red. Whereas, if I look at these little clumps here, these ones are red, but this filament between them is kind of blue. So the galaxies are segregating according to their redness or blueness, which has to do with how old the galaxy is. And so you're learning something about the history of how the galaxies formed. The structure here is telling you, after the galaxies formed, how they were pulled together by gravity. So there's a huge amount of information in this map and the colors of the galaxies about what the history of the galaxies. I can take this map, and this is based on 20 years of observations. This is starting, we're at the center. We're going to zoom out, and we see the galaxies are shown here. I'm now coloring them all red because in the outer regions, our telescope can't see galaxies. We can see quasars, which are supermassive black holes at the centers of galaxies that are shining super bright. And so we can see them further away, and we can make a map even further out. And that's as far as you can go, because the thin line here is the edge of the observable universe. We will never get a photon from further than that. This sphere is the entire universe. And we've mapped a few % of it. That's pretty cool. So as I said, we get a lot of information about the galaxies. We get images like this. And I just want to emphasize, like here we're sorting them by their brightness and their color. And you can see there's all sorts of interesting structures in the galaxies to study. You can do this for a lot of galaxies. I could keep zooming out, but I won't. There are many, many, many galaxies. This is a fraction of a % of the number of galaxies we have data on. And for some of the galaxies, we have a lot of information. So this is one of about 10,000 galaxies where we took really detailed observations. So we have a spectrum of every location within this hexagon. And this spectrum here is showing the inner parts, this top one, and the spectrum here is the outer parts. And what I want you to see, or to know, is that these inner parts are red and old, and the outer parts are blue and young. And the inner parts have stars which are very enriched in things like oxygen, magnesium, calcium, iron, whereas the outer parts don't. So these are all clues to how the galaxy formed, because the galaxy formed by gas flowing in, roughly pristine gas, just hydrogen and helium, and then the stars formed all the heavier elements. And so you see the progression of that enrichment where the inner parts have been enriched more with these types of elements, stuff like the stuff we're made of, and the outer parts less so. And if you put all that information together, and you're a theorist, you can take the data from our survey and you can try to fit models. And based on those theoretical scenarios, you can run a simulation. Your simulations aren't perfect. You have to make a bunch of assumptions. And it's our observations which guide those assumptions. And when you put all that information together, our observations, the physics that goes into this model, you get a picture of the history of galaxies like this. This is a very zoomed out view on the lower left where you see structure forming. And this is zoomed in to this location in the center. And you see the galaxy forming. And even now you start to see spiral arms. This is actually the dark matter. No, I think this is the stars in the galaxy. And this is the gas. So the story it's showing you, the gas is flowing in. And as it flows in, it starts to form stars. And then the gas undergoes this process of enrichment from the stars, and more stars form that are more enriched. And that progresses, and you end up with a disk-like galaxy, a disk of stars, and a disk of gas, like our Milky Way. And that's the picture. So that takes us up to about 2020. And starting in about 2020, the survey progressed through about 4 different phases, and is currently in its 5th phase. And this is a very Carnegie-heavy phase. The director of SDSS-V is Juna Kohlmeyer at Carnegie. Stephanie Wachter is the project manager. Solange Ramirez was before her. These people helped build the whole system. And so Carnegie has been a huge part of SDSS-V happening. And one of the reasons I got to know this organization really well before I came here. And one of the reasons it's been such a big part of it is a big concentration of SDSS-V has been, we're not going to look at galaxies so much anymore. We're going to look at our galaxy really carefully. The reason for that is that there are other programs which are now mapping the universe on larger scales with larger telescopes. And so they're going to do better at that. But we are going to look at our galaxy really carefully. Now, if you look at it, some of it is visible from the north, but the center of the galaxy is really only visible from the southern hemisphere. To see the whole galaxy, you've got to have an observatory in the north. We already had that. But you also need an observatory in the south. And so you need the Carnegie Observatory at Las Campanas. So this is the really big telescopes down there, the 6.5 meters. And way down at the end of this ridge is the old DuPont telescope. And this is what SDSS is using. One of the things SDSS is using there. The other thing is if you want to cover the whole sky and you want really detailed observations of the galactic plane, you really want to do better than the plates. Because the plates, remember, took 20 minutes to take on and off, right? So we observe for an hour, it takes 20 minutes to take on and off. Can't really do a shorter amount of observations and cover more sky because you're already spending 20 minutes off sky. So you're not going to spend like 15 minutes on sky, 20 minutes off sky. That seems wasteful, right? So you want to be able to go from field to field more quickly. And one thing we know these days is things that do something quickly are robots. Robots are great. We will all be working for the robots. But what these things do is instead of the plug plates, each location in the focal plane of the telescope, there is a robot which has a little patrol area. And it has a fiber attached to it. And it can place that fiber wherever it wants in that patrol area, as long as it doesn't hit any of the other robots, which we're really good about avoiding. And if you can do that, moving the robots around, you don't have to take the instrument on and off. You just move them around. It takes 30 seconds to move the robots. So you can change from field to field pretty quickly. So SDSS-V built 2 of these, one for the north and one for the south. Here's the one that went to the north, along with the people who helped put it together. They did this in like 2020 and 2021. So it was also an interesting time to be trying to build something, but they ended up doing it. finishing this in October of 21. This is the team who helped finish the one that went into the southern hemisphere and then helped operate it. All of this started working in 2022. Here's just a video of the robots repositioning. They start at home in this nice hex pattern, and you'll see them slowly moving to where they're supposed to be. I say slowly, but it does it in about 30 seconds. And slowly and very carefully, so they don't hit each other. Now, there are other things you have to do when you change fields. You have to recalibrate, you have to move the telescope. So it takes more than 30 seconds, it takes about 5 minutes. But still, oh yeah, this is the last plate, the very last plate to be observed. And so sort of like taking the long march down to the focal plane before the last plate observation. I guess they put cartridge 1 on there for old time's sake. But once you have the robots, then you can cover the whole sky. And so this is a map of the whole sky, like a sky map. Each dot is a location of a field, and it'll get darker as we observe it. And we weren't operating at top efficiency for the first couple of years. It takes a while, it's a new instrument to get it right, but then you'll see a couple years in that we really start to get going and start observing the sky quickly. It happens just about now. And you'll see we'll start observing the sky faster. This video extends to September 2027. So it goes up until like a month ago in terms of what we've done, and then it's a projection after that. But by the end of the survey, we will have covered the entire sky. And you can see the concentration of fields and observations here along this line, which is the galactic plane, because we're really interested in the galactic plane. I guess we're going all the way to 27. There we go. I was really happy to see these projections because I was afraid we weren't going to make it. So what that allows you to do is if you want to map the galaxy, this is sort of an artist's rendition of the galaxy. The center is here, the sun is here. This is the map we had from SDSS-4. So, you know, it's pretty good, but it kind of, like this is just a location of where the stars are. And you can see there are gaps, it's kind of spiky. That's because we had a very sparse sampling of the sky. At the end of SDSS-V, we'll have a much more continuous map of this side of the galaxy, the side of the galaxy that we're on. And when you have something like that, you can make maps like this. This now, here's the center of the galaxy. Here's where we are. This is radius along here. And then vertically is the distance from the galactic plane. So now we're looking at the galaxy edge on. And what's the color means, it's the age of the stars there. And so you can see that just like the galaxies that we were observing, you know, with the earlier phases, the galaxy itself is older on its inside and younger on its outside. And it's older up here, away from the plane, and younger at the plane. And these things you can map in incredible detail. And I don't have time to explain this, but you can untangle things even further to show that there's certain categories of stars, shown schematically here, which because of how they're enriched and how old they are and what age and where they are in the galaxy, you can tell that they've migrated. So a bunch of stars around the sun, including maybe the sun, have migrated from the interior parts of the galaxy to the outskirts of the galaxy. So we're like really untangling real details about this galaxy we live in. And again, I'm going to not explain this well enough, but there's yet another part of SDSS that's at Las Campanas, which is imaging the gas. Remember, the stars are being formed from the gas. We know the gas is there because we can see it in the radio, but with optical light, we can also see the warm gas that's being lit by stars. And that tells us a lot of interesting things about how the stars are forming. It also makes some pretty cool images. So remember, Galileo concluded that actually the Milky Band of the Milky Way was just resolved into stars. Actually, a little bit of that diffuse light is coming from gas. Not what you can really see with your eye, but it's there. And our telescopes can see it. So this is an image of the galaxy and the stars. And this is switching to our observations as of probably a year and a half ago in the gas. So there's lots of gaps because we haven't finished this part of the survey. But you can see all these amazing structures. Star-forming regions, supernova remnants, shock waves, all the signatures of stars forming and the effects of stars on the gas around them. Like literally seeing the process of the enrichment of the gas in play. This goes on for a little while. There's a lot of sky. Zooming out a little. And over on the right, you're going to see the Orion region up here. So that's the Orion Nebulae there. And so we have a huge map around the Orion Nebula. And then we've also done the Magellanic Clouds. This is a small Magellanic Cloud, again, just the gas in it, and all the star-forming regions, and this is a large Magellanic Cloud. So that was the end. But after 2027, we're going to keep observing. And we're planning for the phase after SDSS-V, which is starting really soon. It's being led by Keith Hawkins at the University of Texas in Austin. Still going to have a big component involving Carnegie. It's going to do a number of different things I don't have time to describe. But one thing I want to emphasize is that one of the big projects, which is going to involve the DuPont telescope at Las Campanas, is going really deep in the galactic plane and looking at this side of the galaxy. And so explore the hidden side of the galaxy, seeing all the way to the other side. So that's our hope. We got a lot of money to raise, a lot of work to do, but wish us luck. Thanks.